Hello. In this video, we shall be discussing about interference of light rays or light waves. Now, as we have been discussing about the case of wave mechanism of the light. Now, as light travels through a medium, it travels in the form of a wave, and this wave, what it does is it disturbs the particles that are there in the medium. Now, in this case, as you see the wave over here, this wave, there will be particles in the medium at different points. I'm considering those 4 points that I've just drawn. Now, these particles, when these waves will be traveling in that medium, these particles will be oscillating up and down their positions, their equilibrium positions. They'll be oscillating up and down. Now, they can also oscillate to and fro, but because light is a transverse wave, now when a transverse wave travels through a medium, the particles in the medium oscillate perpendicular to the direction of propagation of the wave. In this case, the wave is propagating in the forward direction to the right of your screen. And the particles over there, they are oscillating on the plane of the sheet that you're seeing on your screen. They're oscillating up and down their position. Now, it may so happen that along with this wave, there might be another wave that is introduced into the medium. So let me consider another wave that travels along that medium. Now, I've taken this independently over here, and as it travels, it's not a uniform one, as you can see. Whatever is the position of the particle in that wave, the particle will tend to oscillate in that form. So this is more or less the case how the particles oscillate when this wave travels in that medium. Now consider the interaction of these two waves. Now these two waves, they tend to interact with one another. Now when we consider the interaction, we call that superposition of these two waves. So this is the first wave. It's more or less like this, and the second wave comes in the way of the first wave, or vice versa. The first wave may be coming in the way of the second wave, and as a result of that, what you would observe is something like this. Now, it may so happen that both these waves have different amplitudes. Now, amplitude is the disturbance or the maximum displacement of the particle from the mean position. Now, the mean position is the dashed line that I've shown you in the figure. So, in that case, the dashed line giving the mean position that has been the, from that mean position, the particle has been displaced either to the upward direction or the downward direction. It continues to oscillate up and down as the wave propagates. Now, it may so happen that these amplitudes may be different. Let's assume that this blue one has an amplitude of A1, while this red one has an amplitude of A2. Now, both these amplitudes interact in some way or the other, as they both of them they superpose with one another. Now they tend to interfere, and out of this interference, what we get a resultant, displacement of the particle of that medium. So this particle which was there in the along that dashed line that I've just drawn, this particle now, with the interaction of these two waves, either the particle has gone up because of this top wave, or the bottom wave has dragged it downward. Now, simultaneously acting on that particle, these two waves will produce a resultant. Now, the resultant, obviously, if A1 is greater than A2, now the resultant will be in the upward direction as A1 minus A2. Now, consider the case. Not going to use another ink this time. I'm just being lazy. So, this is the wave, the first wave probably, and this is now the second wave, which is not exactly in phase, but somewhat somewhere there. It has a different wavelength, different amplitude, and many more different things associated with respect to the first wave. Now, at this point, if the particle is observed, the particle is displaced partially due to this first wave to that point, and then It is also displaced to some other distance due to the second dashed wave that I have drawn. Now, this is not perfectly placing the placement of one wave over the other. Now, if I suppose that one wave, the first wave, has traveled like this, while the second wave is exactly in phase with the first wave, exactly in phase. Just giving you a little difference so that you can identify them. So this is the case. Now the particle would have oscillated to that point due to the first wave, and it will also oscillate to that point due to the second wave. But what happens is that when these two interact, they interfere with one another. The resultant wave is, however, not like this. The resultant wave is something different. It is going to be an addition of both those amplitudes. So this addition of amplitudes results in this kind of a wave, which is A1 plus A2 being the new amplitude of the new wave. So the resultant wave, or the resultant displacement of the particle that lies in that medium where the two waves interfere, is affected due to the interaction of these two waves. And the interaction here, I have shown you the physics point of view. Now, we will also consider the mathematical approach to this, where we'll be considering two different waves and given by two different equations. Now, the equation that is related to a wave is actually determined by the displacement of the particle which is there. Now, this particle supposedly it's oscillating along the y-axis, right? And with that displacement along that y-axis at a given instant of time, we can determine. Now, as you can see that these waves, these appear like simple harmonic waves. So the harmonic waves are usually represented by the sine and the cosine functions. To our advantage, we'll be using the sine function to represent the displacement equation for a given wave, and for those two waves that we have taken as example over here physically. But mathematically here we'll be placing these two equations. So y1, let that be the equation of displacement of the particle in the medium due to the propagation of the first wave, which is given by y1 is equal to, let's say the amplitude is a1 sine omega times of t. Omega t is the angular displacement at that given instant of time t, when omega is the angular frequency with which the wave moves. Now y2 is supposedly the displacement equation for the second wave, which is, let's say, uh, ahead by a phase phi. We do not know what that phi phase is. We have just given uh, a variable representation for that phase difference between those two waves. Now, in this case, obviously, as we can see over here, the phi phase is actually 180 degrees because they are exactly opposite to one another. While in this case, they will be exactly in phase with one another, where the phi is 0 because they are exactly moving in the same manner. They are going up and down in the same instant of time. The principle of superposition that states that the resultant wave that we are going to get out of those two uh, waves when they interact with one another, we have y to be equal to y1 plus y2. Now y is equal to y1 plus y2 gives me, well, I can expand that equation, that sine function, and from the trigonometric condition that I have, that is sine omega t cosine of phi plus a2 is the common term for that, sine phi cosine of omega t. What I will be doing is that I will be taking the sine omega t term to be common, and so what I have is a1 plus a2 cosine of phi times of sine omega t plus a2 sine phi cosine of omega t. Now out of that, what I do is I consider this term that is carrying a phi and also this term which is carrying a phi as two different terms. Let's take them as a common amplitude in this case. Let's assume that the amplitude is let's say A. So I take this as A cosine of theta. Theta is some angle. We do not know what that represents right now. And then this one as the same amplitude A, but this is sine theta. So assuming these two conditions that we have used, what we do is we continue with the equation. That's all we can do right now. So this is A cosine of phi, A cosine of theta, sine omega t, plus A sine theta, cosine omega t. That's again coming in the sine form. So A can be taken as the common term, and we have sine of omega t plus theta. Now what I have done is that I have again converted that to a single sinusoidal function or sine function, and that is the equation for the resultant wave. Now the amplitude of the resulting wave is something different, obviously. Here we can see the amplitudes changing in both those cases. Also here, even though I haven't really mentioned how they are changing, but they are changing in fact. So we can determine this A because we have those values of A sine theta and cosine theta. Now A is obviously equal to A squared sine squared theta plus A squared cosine squared theta under root. I'll avoid the root, I'll just keep it as A squared. And then because of that, what I know is that A squared is going to be, well, the square of all those terms that we have. That is A2 sine squared phi plus A1 plus A2 cosine phi squared. And squaring of those terms, what would that lead to? Well, that is A2 squared sine squared phi plus A1 squared A2 squared cosine squared phi plus 2 times of A1 A2 cosine of phi. That's the square term of the second one. So A2 square sine square phi, A2 square cosine square phi is simply A2 squared. Let me write A1 squared first. So then I have A2 squared, then I have 2 A1 A2 cosine phi. So as you can see that the resultant amplitude is actually being treated as the vector sum of those two amplitudes which have an angular difference between them in the form of phi. This is exactly the vector equation that you would get as the resultant of two vectors when they are separated by an angle phi. So this is actually the vector sum that we are getting. So it won't be wrong if we represent this principle of superposition that I have written over here in vector form. So y is equal to y1 plus y2. Now for simplicity we drop the vector as of now because we have obtained the magnitude, that is the square of the amplitude. Now what we know is that the intensity of a wave that is directly proportional to the square of the amplitude. So that means we have the resultant intensity as proportional to a squared. Now the individual intensities due to of those two waves that we have considered, that can be taken as I1, which is proportional to A1 squared, and I2, which is proportional to A2 squared. Now the proportionality can be obviously taken care of. We can take a k in that, which is a constant of proportionality. Now I is equal to k times of a squared. Similarly, I1 is equal to k times of a1 squared. I2 is simply k times of a2 squared. Now out of those things that we have done over here, what we can do is we can multiply a k completely into these two equations. And what we find is that the resulting equations that would give us the intensity as I, that is equal to, now k times of a1 squared is going to be I1, k times of a2, k being taken into that bracketed term, that gives me I2, plus, well, the k can be taken inside and where they can be divided as root over of k and root over of k times of a1, root over of k times of a2. That would eventually give me root of I1, root of I2 times of cosine phi. Now this is the resulting intensity of the resultant wave when we have two different intensities I1 and I2 interfering with one another. This is the term interference that comes into picture. Now, had they not interfered, they would have remained individually and impacted the medium individually. That is the intensity at that in that case without interference. Without the interference, the intensities would have been I1 plus I2, as simple as that. But with this intensity, now you have a phase difference that is getting involved. And as a result of that phase difference, you will be having a different scenario altogether. There will be a vector sum of the intensities in that case. Now, also what we can also guess is that the amplitude is obviously would have been just A1 plus A2, or simply different A1 and different A2, because the intensities are different. So A1 and A2 would have been individual amplitudes of individual waves. Now, because of that interference, we are having a relation of amplitude as well. That is A, well, I have taken the square of it. Well, I can write it simply as A to be equal to the root over of A1 squared A2 squared plus 2A1 A2 cos phi. Now, what we need to look at is that the value of that angle or the phase difference that they have between them, that is phi. Now, that is a very important factor when it comes to interference of light. Now, if that factor phi is completely zero, which means they are in phase with one another, then what we would have had, well, cosine of 0 is obviously 1. So that would have resulted in this kind of a scenario where we had obtained A to be equal to, from this equation that we are getting, A is equal to A1 squared plus A2 squared plus 2A1 A2, cosine of phi is 1 in this case. So considering this situation over here, A is simply equal to A1 plus A2 squared under root, which is equal to A1 plus A2, which is exactly what we have written over here. And what if they are at an angle of 180 degrees, completely opposite in phase? Now this one above, this one I am calling it as the maximum amplitude. Now if they are at a phase difference of 180 degrees, what happens to the intensity then? Well, the intensity, because of cosine of phi for 180 degrees is -1. So we will be having the most minimum intensity. And for the cosine of phi being the maximum value, we will be having the maximum intensity corresponding to the maximum amplitude over here that we have obtained. And as far as the minimum amplitude is concerned, we know that A1 squared plus A2 squared, cosine of 180 is minus, so minus 2A1 A2, that gives me A1 minus A2 squared under root. So this is A1 minus A2, which is exactly what we have written over here. So what that means is that this interference of these two waves that determines the value of the intensity of energy distribution. Intensity corresponds to the energy distribution. The greater the intensity at a place, the intensity of light, the greater is the optical energy that we are getting. So the intensity becomes very less, or goes to the minimum, if those two waves which are interacting the light waves, they are completely out of phase, that is at an angle of 180 degrees with respect to one another. And the intensity is a maximum when they are interfering by being in phase. So because of this low intensity, what you can say is that they have interfered with one another destructively. While the case where they have interfered with one another to give the maximum amplitude, they have interfered constructively. So that's the phenomenon of constructive and destructive interference. Now we'll be dealing with more about this topic on constructive and destructive interference and how this interference determines the redistribution of intensity, although we have already seen that how the intensity is varying due to the interference, but also we'll be observing that how this intensity is getting distributed in that region where those two are interfering, and as a result of this distribution how the energy is getting distributed. So more or less what we are going to say, or what we are going to state, is that interference of light is simply the redistribution of intensity which eventually leads to the redistribution of energy, optical energy, light energy, in that given medium where the two waves are interacting or interfering with one another. But that is to be discussed in the next video. Till then, thank you for watching.